Here is a problem that you may or may not find challenging. We're given the pH of stomach acid, it's 1.5, and we're given aspirin, the acetylsalicylic acid, has a pH or pK of 3.5. It's a weak acid, that's the pK of that. All right, a few questions based on this stem here. The structure of aspirin is shown in the next slide, and circle the proton you think is the acidic proton. Let's look at the structure of aspirin. Here it is. Which one do you think corresponds to the acid? Well, we have three choices here. Let me change the ink color to black so we can actually see what I write here. All right, here's a choice of protons there. One of those. Here's a proton here. And here are these protons here. Maybe you remember a little bit of organic chemistry. Let's look at these protons. Okay, and I'll switch colors here. All right. So this stands for a CH3. I'll just write that HHH like this. So those protons there are CH3. Let's look at this proton down here. This is a benzene ring, carbon, carbon. There's an H coming out here. There's an H coming out here. And double single bond, and so on. So those are another kind of H's. And finally, we have these H's here, which I'll draw down here. This is a carboxylic acid group, which you will learn in organic chemistry. And the fact that I call it an acid group means that is the proton. But let's see if we can see that. So here's, I'll draw the structure here. There's an OH there. And then this is connected down there. So those are our three choices of the kinds of protons we think can be acidic. Well, this is a shared bond here, a covalent bond. Yeah, maybe. But look at this. The oxygen is more electronegative than H. So this will be a partial negative charge here, and there'll be a partial positive charge here. What is happening when that happens? Well, you're taking electron density away from the hydrogen atom and putting it on the oxygen, and you're weakening this bond here, one way to look at it. So in fact, this proton, the one on the carboxylic acid group, is the acidic proton. All right, let's talk about the next question. What is the predominant form, acid or base, of aspirin in the stomach? And explain your answer. Let's just write down the acid-base equilibrium that occurs in the stomach. Acetylsalicylic acid, weak acid. I'll denote that by this shorthand notation here. That will dissociate into an H plus and an A minus. We write down the equilibrium expression for this, Ka, products, which is H plus, which are H plus and A minus, over reactants, HA. Now, in the stomach, we said that the pH in the stomach is 1.5, and the pKa of acetylsalicylic acid is, what do we say there? 3, I have to go back up here. I forgot what the answer is, or the question, let's see, 3.5. Okay, 3.5. All right, so what does that mean? This means the hydrogen ion concentration is 10 to the minus 1.5, and the Ka is 10 to the minus 3.5. Well, this is interesting. We can sort of play around with this equation here, or these two equations. What would happen if the acid were half ionized? What would that mean? That would mean that half of the unionized acid had dissociated into H plus and A minus. That means, for instance, if you started with 1 molar here, this would end up half molar, and this would end up half molar and half molar. So if it's half ionized, this means that the concentration of HA is equal to the concentration of H plus, which is equal to the concentration of A minus. That's interesting. Let's put that into this equation here. So if half ionization, the HA and the A minus concentration are equal, half ionization, that means that the Ka is equal to the H plus concentration, And or another way to look at this is the pKa at half ionized, is equal to the pH. Okay, so right when the pH is equal to pK, you're on the balance. If you can go one way or another. When the pH is equal to pK, when the hydrogen ion concentration is equal to the HA concentration in equilibrium, you're half ionized. Now the question asks, what's the predominant form, acid or base? So now we're going to ask the question, okay, Ka in this problem is 10 to the minus 3.5, and the pH in this problem, or the hydrogen ion concentration, is 10 to the minus 1.5. This is a bigger number than this. So what you've done is increase the hydrogen ion concentration over and above the concentration that you maintain a half. So by Le Chatelier's principle, by having this greater than the amount that's half ionized, you shift the reaction over here. So in fact it's the unionized form that is predominant in the stomach. It's the acid form rather than the base form. Hope that made sense. Come to an office hour and for more additional explanation. All right, so the answer to this is the acid form. Okay. Now let's go to the next question here. Typically aspirin is absorbed into the bloodstream through the gut, so it gets in your stomach and then it goes to your gut and then it gets into the bloodstream and then it does its action on various sites of inflammation. So now, what is the predominant form of aspirin in the blood where the pH is 7.4? Well, remember at that half point, Ka is equal to H plus concentration at equal base and acid forms. And the equilibrium here is HA in equilibrium with H plus and A minus. Okay, so the concentration here, the pK, or remember the Ka for this, the Ka doesn't change when the aspirin goes from your stomach to your bloodstream. Ka is the same, only depends upon temperature, and let's assume that the temperature in your stomach is equal to the temperature of your blood. So Ka was 10 to the minus 3.5, and now the H plus concentration is equal to 10 to the minus 7.4. Now at equal acid and base concentrations, Ka would equal H plus. So at equal acid and base concentrations, the concentration of H plus, when they're equal amounts of acid and base, would be equal to, in this case, Ka is 10 to the minus 3.5. The fact that H plus is not equal to that, in fact it's less than that, means that this concentration has decreased relative to the amount that would have equal amounts of acid and base. If you decrease this concentration, the reaction will shift over to the right, and therefore producing more of the base form compared to the acid form. So the predominant form is base in the blood. So it enters your stomach as an acid, but once it gets into the blood, because of pH equilibria, the blood maintains a pH of 7.4. Now you have the base form of acetylsalicylic acid floating around, getting into your joints and reducing inflammation. All right, let's go to another problem here based on that. Okay, a general rule in small molecule drug delivery. All right, this is when you're doing drug discovery and so on. If you want to get a drug inside of a cell, you have to have the uncharged form of the drug. And then when it gets inside the cell, if you can convert it into a charged form, then the drug will stay inside the cell, because the cell membrane is less permeable to charged species compared to uncharged species. All right, so what would be the ratio of the charged to uncharged form of aspirin in the blood? All right, so, would it get into cells or would it not? In other words, is there a lot more uncharged form, in which case it wouldn't get into cells as quickly? or is it the more charged form won't get into the cells, or is it a more uncharged form? Let's be quantitative about this. All right, so we're going to write down what the equilibrium is. Ka is equal to the concentration of H plus times the concentration of A minus over the concentration of HA. Now what we want in the problem is the ratio of the, I forgot what we want, so the ratio of the charged to uncharged form of aspirin. So the charged form of aspirin is A minus, the uncharged form of aspirin is HA. Well, from this equation, if we just divide both sides by H plus, that's just equal to Ka divided by the hydrogen ion concentration in blood. Well, we know what these two things are. Ka is 10 to the minus 3.5, and in blood, hydrogen ion concentration is 10 to the minus 7.4. And if we put this into our calculators, we get 7.94 times 10 to the third. So that means that about for every 7 or 8,000 molecules of HA, only one of them is in the protonated form, and the others are all in the base form. So mostly base, almost all base if you look at this number here. All right, well, that's how to do that. Maybe challenging problem. Hope you followed that.